streaming set up.
That's over there. I don't know where the button is yet, but we'll figure it out.
Okay, you can roll the show then.
Okay, so let's begin. Wait a second. Still trying to find where all the windows are. Yes, welcome to the final day of condensed matter in the city. A few of us, 3 of us, I believe, are live here from Imperial College London. Oh, 4 of us now. Hi, Derek is out of jail. Yes, for this final day, so we have 2 excellent talks, and without further ado, let's just go into the first one. So the first speaker is Adam Smith from the University of Nottingham. So Adam got his PhD in 2018 from TCM in Cambridge under Dmitry Kurazin. Then after some postdocs in Imperial and Munich, got a prestigious fellowship from the Royal Commission for Exhibition of 1851, which he's taking up at Nottingham. He works on the interface between quantum computing and quantum materials, doing all the sexy stuff like information, topological systems, quantum simulation and stuff. And today he's going to tell us about skeletons in the phase diagram, matrix product state solvable models connecting topological phases of matter. So without further ado, please begin, Adam.
Brilliant. Thank you very much for the very kind introduction. And thank you to all the organizers for organizing this very nice workshop and keeping it going through COVID, and for giving me the opportunity to talk about this work. So just to confirm that you can all see this, right? It's still showing.
Yes, it's good.
Yeah. Okay, great. So yes, as Sam pointed out, the title of my talk is Skeletons in the Phase Diagram, and the maybe more informative title is Matrix Product State Solvable Models Connecting Topological Phases of Matter. So before I start, I'd like to thank my collaborators. So Nick, who's in Oxford, Julian, Bernard, and Frank, who are in Munich, Ruben, who's now in Harvard, and also Andrew Green, one of the organizers, who's at UCL. Okay, so just to give you a brief outline of how the talk's going to go, I'll tell you a bit about the topological part of my title, the MPS part of my title, and then I'll move on to a simple example of this MPS skeleton that I'll tell you a bit more about, and how we actually were able to implement this on a real quantum computer. So this connects back to Frank's talk a couple of days ago. Then I'll move on to the more general idea about this MPS skeleton and how it all works, and I'll end with a bit of an outlook. Okay. So as you will have heard, I think several times over the last couple of weeks, topology comes in many flavors in many body physics, and I'm going to be focusing on one of these, which is symmetry protected topological order. So the idea here is that we can have phases that on the face of it are trivial. Sorry, what was that? No? Okay. So we have phases that are on the face of it trivial, but if we have a symmetry, then they can split into distinct SPT phases. Okay, so the idea is that we have a symmetry that is protecting these phases, and if we break the symmetry, then these phases are no longer distinct. So there are famous examples of these that you've probably all heard about. There's the AKLT state and model. There's the Haldane phase, of which this AKLT is a model example. We have the cluster state, and we also have topological insulators. Now, one of the interesting things about these SPT phases is that instead of being characterized by local order parameter and symmetry breaking, they're instead characterized by string order and string order parameters. So an example of what this might look like, it might look something like this operator down at the bottom. We have a long string of symmetry operators, these UJs, and then we can have some operators that terminate this long string, which are essentially going to select which phase we're going to get the signal from this order parameter in. Another interesting property and potentially useful property of these systems is the edge modes, localized edge modes that we get when they are in finite systems. So this AKLT model example, this is an example of a spin 1 chain. But if we put it on a finite system, then we end up with dangling spin 1/2 degrees of freedom at the edge. And a lot is known now about these FBT phases, and they can be classified in terms of group cohomology. Okay, so that was a super quick overview of the topology part of this. The other part of this is the matrix product states. So these came about and are useful because they are efficient representations of lowly entangled states. And this is useful because ground states are typically lowly entangled. So we have the area law in 1D and also higher dimensions, which means that the entanglement doesn't grow with the system size. In 1D, in fact, it is constant with system size. It's determined only by the correlation length. And so this means that the entanglement is low.
Adam?
Yes?
Can you remind us what group cohomology is, please?
What group cohomology is? I probably would do a terrible job of reminding you what this is.
Because you put it in as something important. So
sorry? Sorry, I couldn't hear you very well there.
Yeah, it seems important, this classification. So could you say a word about it, please?
Well, I don't really know what to say. I wouldn't want to go too much into detail about these group cohomologies.
I mean, is it fair to say, sorry for interrupting, is it fair to say that in this 1D case, it's basically telling you about the symmetry transformation properties of the edge states?
Yeah, that's a very good summary. Thank you. Yeah, okay.
Okay, go on.
Is it okay if I carry on?
Yes.
Okay, so in these matrix product states, they're useful because we can represent these lowly entangled states. And just very quickly how this would work. If we have a wave function psi, then it's characterized, well, it's all the information about this state is contained in the probability amplitudes, which can be represented as a many-leg tensor, essentially. You have psi, J1, J2, J3, and these J1, J2, J3, these are the physical degrees of freedom. And now instead of this horribly large tensor, we can split this up into a product of matrices. And when we've done this, these products, so I mean, hopefully you've seen diagrams like this, but these products with these bars connecting the matrices, we can now truncate the size of these matrices, or as it's called in MPS, we can truncate the bond dimension. And by doing so, we obtain a much reduced representation of the state, and it's because of the low entanglement, this is accurate for these ground states. The important thing to note is that the bond dimension, the size of these matrices has to scale exponentially with the entanglement. Okay, so these are extremely powerful for understanding ground states, and we can use DMRG or TBD to optimize these MPS to get the ground states. Now, what I'm going to talk about is cases where we can actually represent states exactly by using a low bond dimension. So typically when we do this splitting into matrices and truncating the bond dimension, this is an approximation to the state. Now, there are cases where this low bond dimension actually gives you the exact state, the exact ground state of the Hamiltonian. And one such example is this AKLT state and the AKLT model. The ground state is actually an exact MPS with bond dimension 2. And in these nice lecture notes, there's a very nice picture for showing how to get the MPS from the AKLT state. Essentially, you can understand it by splitting the spin 1 degrees of freedom into 2 spin halves, creating singlets, coupling them, and then projecting onto this spin 1 space. And essentially, by a redrawing of this picture, we can see that we end up with a matrix product state. And now these bond dimension 2 comes out just from this, these singlets connecting these spins. Okay. And actually, historically, the development of MPS and SPT phases was quite closely linked. And a lot of the properties of SPT phases were made a lot clearer by analyzing the matrix product states. Now, the AKLT MPS is exact, but it's typically thought of as an isolated exact MPS. So it's a special toy state which is in this SPT phase, in this Haldane phase. One question that you might think of, or at least in hindsight for us, is are there continuous MPS solvable paths? So rather than just isolated points, are there continuous paths that go through the phase or even across phase transitions into different phases? And as you'll probably have guessed, the answer is yes to both of those.
Can I just ask a question quickly?
Yes.
So by MPS solvable, you mean something that has a finite one dimension and is exact? Is that what you mean by MPS solvable, or are you going to explain?
Yes, yes. So that is a term I introduced without explaining. MPS solvable, we mean the Hamiltonian has a ground state which is exactly representable by a finite bond dimension MPS.
Okay, thank you.
Thank you. Right, so now with that little bit of background, let me show you a simple example, which I'll come back to again. And this simple example, we were actually able to put on a real quantum computer. Okay, so let us consider this Hamiltonian. And if you're interested, it's protected by parity and time reversal symmetry. This Hamiltonian consists of 3 terms. So we have an Ising coupling, this ZZ, we have a magnetic field, and we also have a cluster term. Now this Hamiltonian has 3 different phases depending on the parameters, and that's what we've shown in this kind of triangular plot. We have the trivial phase when if we have a dominant magnetic field. We have the symmetry broken Ising phase, and we also have an SPT phase, which has the cluster state as one of the points when we just have this cluster part of the Hamiltonian. Now, this phase diagram actually has one of these MPS solvable paths through it. As was originally realized in this paper in 2006, actually, before they realized it was an SPT phase that they were going through, it was realized that they had this MPS path going across a phase transition. And this path is parameterized like so. We'll come back to where this parameterization comes from and why it's important a bit later. But what this parameterized path is this thick black curve through the phase diagram. So all along this curve, the Hamiltonian is MPS solvable, and the ground state has an exact MPS with bond dimension 2. And one of the cool things about this path is it actually goes across a phase transition. So we go from the trivial phase to the SPT phase. Now that might ring alarm bells for some of you. How can we go across the phase transition if we have a fixed bond dimension. And actually this point sits at the intersection of two critical lines and is itself not actually critical. And so this point, we actually just get a cat state, which can be represented by this bond dimension 2. Okay.
So sorry, can you explain?
Yeah.
Can you explain better what you mean by cat state there?
So the cat state here is really, it's like a G8Z state. It's just all spins up plus all spins down. So it's, this Hamiltonian is a spin half model, and this cat state is just the state of all spins up plus all spins down.
Okay, thanks. There's also a question in the chat by Edmund Orignac. Are you able to unmute and ask your question?
Yeah, so I wanted to know if this model could be mapped to a free fermion model by a Jordan linear transformation.
Yes, so this model can actually be mapped to a free fermion model, and we will come to that a bit later when we consider the more general case that I'm going to look at. These will actually be a larger class of free fermion models that I'll be looking at. So yeah, this whole diagram in some sense is all solvable. But we have this special MPS-solvable path. Free fermion solubility does not necessarily imply this MPS solvability.
Thanks.
Thank you. Any other questions at this point?
I don't see any just now, okay. So continue.
Thank you. So yeah, so we have this phase diagram now, and we have this MPS solvable path, and this was realized by others, and we'll kind of shed more light on this a bit later. But the next thing we did was actually put this on the quantum computer. So I want to tell you a little bit of how we did this. And the first step is to realize that matrix product states we can actually map to certain quantum circuits, to sequential quantum circuits. Now, this is particularly simple for bond dimension 2 because it's exactly this type of circuit. We just have 2 qubit gates that are applied essentially one after another in a sequence. This does actually generalize the higher bond dimension, but then we need larger unitary gates. And just to sort of see how this works, you can regroup this circuit, and you essentially end up with a single qubit wire connecting these blocks, and this single qubit is this bond dimension 2. It takes a little bit more work, but you can show this is actually a general MPS of bond dimension 2 as well. And with this in mind, this connection to MPS, you can use some of the insights from MPS, and we can represent states in the thermodynamic limit as well. Okay, so we have infinite MPS. We can also do this with quantum circuits. And yeah, this picture basically showing you how this works. If we want an observable from part of this infinite chain, then this unitary circuit, everything below this black box is just going to cancel because they're unitary gates. Everything above this black box is just going to be a repeating element, this blue element, which is the transfer matrix. And just like MPS, we can terminate this with the eigenvector of this transfer matrix. Okay, so this is something we're going to use.
Piers asked, can you explain a bit better the meaning of your circuit diagram blocks?
Yes, sorry, that is a good point. So here, what this circuit diagram means is we start our quantum computer, for instance, in the all up state or the all zero state. Then these black lines are the wires, and the wires, this is just essentially the qubit going forward in time. And then these blocks entangle to qubits. Now this diagram up here, all I've done is just redrawn this in a more suggestive way, and then essentially drawn a box in a way that I would like around these different elements. And you can see that coming in and out of these guys is essentially one of these qubit wires. I hope that clarifies a little bit.
Yeah, so what specifically is the unitary transformation the blocks represent?
So actually, this is a general 2-qubit unitary. So it's, yeah, these blocks for a general MPS would be a general unitary acting on 2 qubits. So it's a 4x4 unitary.
But what is it in this case?
In this case, it looks like this guy.
What does it do? What is the matrix?
What does it do? Sorry.
It's a variational ansatz, right? I think.
So in general, yeah, in general, it's variational, right? We have to choose the right unitary. So yeah, it's the space of all 4x4 unitaries, but we have to choose the right one to get the right state. In this case, yeah, I could write down the matrix, but what I am writing down instead is in terms of native gates that will be useful for the quantum computer. So if you apply this particular set of gates, this will give you this black path that I was talking about in the previous slide. Is that clearer?
Yeah, can you just remind us what W, V, and X mean, and H and R?
Yeah, so I don't have this anywhere here. This you'd have to look in our paper. It's more complicated than necessary to include here, but well, okay, so X is just like a Pauli X, H is a Hadamard, R is some rotation, which I've not included here because it has some angle that you have to parameterize. And then these gates here, the W and V, these are controlled operations. So basically, I rotate the second qubit depending on the state of the first qubit. Okay, and now these are all different 2-qubit unitaries or 4x4 matrices. And this particular sequence will give you the path that I was talking about.
Okay, thank you.
Thank you. Any other questions about this? I realize I've been quite brief on this. More to just convince you that this mapping does exist, and if you go through the details, you can work out what these gates should be. And actually, if you have a general MPS of a higher bond dimension, then you can get these unitaries by just putting it into canonical form. If you put it into right canonical form, then these unitaries are exactly the matrices of the MPS. Okay.
Cool.
Okay. Great. Yes. So then the next step we did was we have this infinite state that we're now representing. We put it on a finite number of qubits by using this trick from MPS. And then we have a particular decomposition in terms of the gates that I can actually implement on the IBM quantum computers, which is what we used in this case. And then I can show you some results from the actual quantum computer. And yeah, maybe if you saw Frank's talk early in the week, then you will already, have had a warning about what you should read into these results. So they're not as good as you might expect, but we can still see a phase transition. So on the left-hand side, what I'm showing is the energy density. The gray curve is the exact results, and the points are the experimental results for different system sizes. So you can see it's getting worse as I increase the system size because basically the circuit depth and the amount of time I have to run the quantum circuit is increasing, and the errors are getting worse. On the right, I'm showing some of these order parameters that I talked about. So it's essentially a Pauli string in this case, 2 particular Pauli strings. One of them is non-zero in the SPT phase, that's towards the left, while the other one is 0. And then on the trivial side, they're flipped. So the top one will become 0 and the other one will become non-zero. The important thing to see here is that we can actually see the transition for the smallest lengths of this order parameter. But as we increase it, then actually it goes away because of the noise in the system. So this is kind of showing where we are at the moment with quantum computers. but with better devices, then we might be able to see more interesting transitions than this simplest case. Okay, so that's the simple example I wanted to show you. I now want to tell you a bit more about our stronger, more general results about this MPS skeleton. Okay. So as you might guess, that this black line that we have in this path, this is what I'm going to end up calling an MPS skeleton, and hopefully you'll see why. That's a nice name for it. Okay, so before we state the results, I just want to set the stage. So what we're actually going to consider are essentially free fermion models in a particular symmetry class. So consider a chain of Majorana operators, gamma n and gamma tilde n, and we'll consider Hamiltonian terms of this form. So basically a gamma tilde with a gamma. And now the BD1 class of free fermion Hamiltonians is of a general Hamiltonian of this form. Basically, you sum up these terms where the index between these gamma tilde and gamma is parameterized by alpha, and you can sum these up, and this is the BD1 class. In the top, I show you what this, I include what this BD1 class is. Basically, it's positive under all of these symmetries, this chiral, parity, and time reversal. Now here I was talking in terms of free fermions and Majorana operators. If that's not too familiar to you, you can think in terms of spin language instead. So these H and alpha terms, they look like these. These are essentially Pauli strings, and they're generalized cluster operators, essentially. Now, so this class of Hamiltonians, this includes models we're familiar with, like the Ising model, the transverse field Ising model, and generalized cluster models.
Can I just ask a question here?
Yep.
So the transverse field Ising model has a magnetic field, so naively you think it isn't symmetric under time reversal, but what you're saying is there's a time reversal-like operator that it is symmetric under.
Yes, that's correct.
Correct? Okay.
Yeah,
so it's not real time reversal anymore, but...
Yeah, I think here it's essentially just complex conjugate. It's a real Hamiltonian.
Okay, thank you.
Yeah, thank you. Right, so then one neat thing about these Hamiltonians is that a lot of information about it is encoded in a polynomial that we can construct in the following way. We take these coefficients, these T alpha, and we multiply them by Z to the alpha. Now this defines a Laurent polynomial. It can go from negative whatever to positive whatever. So this is a Laurent polynomial, and from this we can extract a lot of information, such as the ground state energy, and as we'll come to, you can also show when the ground state is MPS solvable, when we have an exact MPS. Okay. Oops. So now we come to the results, and please don't try to read all of this. I just pasted this from the paper, and I just highlighted a couple of the main things that I want to point out. So we have two main results here. The first one is basically saying that in certain cases, we have an exact MPS as the ground state. And these cases are when this polynomial that we introduced, this f of z, when it is of this form. So essentially, it's the square of a polynomial, and we've pulled out some factor of z to the p. Okay, so if you can get your polynomial f of z into this form, then you have an exact MPS ground state. And furthermore, the bond dimension of this MPS is going to be set by the range of the Hamiltonian, essentially. So it's more precisely, it's the range of the Hamiltonian divided by 2, rounded up, is the logarithm of the bond dimension. So actually this applies a little bit more generally. So this also holds if f of z is equal to plus or minus this, this form, also multiplied by h of z, where h of z has this property that as a function of z and of 1 over z, h is the same. Okay? If we have this factor of h of z, then h actually does not change the ground state. Okay? So we're free to add this h of z without changing any of this. So that's the first result. The second result is actually the construction of this MPS. So not only can we show the existence, we can actually show you how to construct this MPS. And to do this, we have to introduce some algorithm that takes these, basically these polynomial coefficients. And then with these coefficients, we essentially come up with a formula of how to build up this matrix product state. Quite simply, how this works is we start from some fixed point ground state, and this is set by this z to the power p part of the polynomial. And then we apply a sequence of layers, which these operators m1 to md, which look like this exponential minus beta times some Hamiltonian. And these Hamiltonians are of this form. If I go back, yes, this I to the, I times gamma tilde gamma. Now this maybe looks a bit familiar. It looks a lot like imaginary time evolution. And actually there is a way of interpreting this result as a sequence of imaginary time evolutions. But I encourage you to have a look at our paper to see that. Okay. Right. So let me tell you a bit more. Let me go into some more examples. Like these are maybe a bit abstract and definitely too many words for a slide. So let me go and revisit this example that we had and put on the quantum computer. So the polynomial in that case actually is just the square of a polynomial g of z. Okay, so I've parameterized it a little bit differently here. Rather than using a g, which I used previously, I've used lambda, but it's actually of this form. So our result holds in this case, and so we can actually find this MPS. So that's the result 1. We actually know that there exists this MPS. And now using result 2, we can apply this algorithm to get these new numbers B1. Again, I don't want to say too much about them. They're just the inner workings. But what it means is that I can write down the ground state as this product. Okay, so now the fixed point ground state, this psi 0, is just the all up state or the all down state. I can't remember which convention I'm using here. And then we have a product of gates of this form. Okay, so now I can actually draw this pictorially, and we get again this sequential picture, this sequential circuit, but now these gates, these blue blocks, are not necessarily unitary. Okay. Right. Yeah, so now again, what you can do, once I've drawn this circuit in this way, you can just group these elements, and you can see that this is an MPS. So if I extract this repeating element, it looks like this. You have a leg going in, a leg going out, and you have a physical leg. So this block is the matrix of our matrix product state. Okay, so with our result now, we can see where we can find this line, and we can actually see how we can get this MPS, how we can build this. One extra thing our result tells us that wasn't in the previous example is that there is another line, this blue line, which is also MPS solvable. And this is because it actually factorizes like so. We have z times h of z, where h had this property that I told you about, this h of z equals h of 1 over z. And in this case, the ground state is just this cat state all along this blue line. Okay, So just one more complicated example. I can write down a higher order polynomial. So again, there'll be a Hamiltonian associated with this. And now what I can do is I can search for these paths through this phase diagram that are MPS solvable. So in this case, we actually have 3. We have this blue line in this phase diagram. In this case, it looks like this, z squared times g squared. And actually, this case is just the same as previous, but now we have this extra factor of z squared in front. Okay, so the physics is still the same, but some of these, like the winding number, for example, has changed in these different phases. Yeah, and then we also have 2 other examples. In this case, we have this red line, and we also have this orange line. Okay. So this is starting to look more like a skeleton. We have all of these exact solvable paths that are kind of threading or going through this phase diagram. And then, yeah, the rest of the phase diagram is kind of like the meat on the skeleton, so to say. Right. So one of the nice thing about this skeleton or these paths of MPS through the phase diagram is that they're actually dense. They're not, although it doesn't look like it here, they are actually dense within this class. So to illustrate this, let's consider the transverse field Ising model. The Hamiltonian looks like this, and the corresponding polynomial is not of the form where our result holds. Okay, so it's not the square of a polynomial. However, we can come up with a series of MPS-solvable Hamiltonians that have the transverse field Ising model as a limit. Okay, and these are of this form. Basically, what we've done is we say that f of z is equal to the square of a function, and that square would be a square root. And now by expanding the square root as a polynomial, we can come up with these MPS-solvable Hamiltonians. Right, and then what we can do is we can increase the order of this, this g of m, get closer and closer to this transverse field Ising model, and then we can actually do a number of neat things. We can extract critical exponents, for example, from this series of MPS. So here we show how the order parameter is scaling as a function of the energy gap at the critical point, and we can extract the known result, but now through a different method. But this is actually an example of a more general fact that actually any state in the phase diagram we can get arbitrarily close to by using an MPS-solvable Hamiltonian. All right. So,
okay, so can I ask a question here?
Yes.
Yeah. So is there any special property of these MPS-solvable points, or this huge set of them, other than they happen to be MPS-solvable? Are they typical in terms of the phase diagram in all other properties?
So they do have a number of special properties, which I'll come to, or I could say a little bit about now. So, for instance, one of them, one of them is that most of them, or some of them actually, can be represented as unitary circuits. So actually all of them can be, but some of them even more simply can be turned into unitary circuits. And this could be very useful for instance, using quantum computers. I'll say a bit more about that because it may not be clear how we could get an advantage, but there is actually potential for an advantage here. Another thing is that you can compute correlation functions exactly using these MPS functions. Okay, which is
okay, but actually just my question was a little different.
Okay.
That if you take, for example, an integrable model, then of course we often use these as things that we then can calculate everything with.
Yep.
But if you take a generic non-integrable model, you know that many of the properties you find in integrable models don't hold over. For example, things like thermalization or whatever.
Yes. Okay.
And this is the question that you're saying you may be arbitrarily close to one of these MPS solvable states, but are there properties of this MPS solvable state that will not go over to these arbitrarily close points?
That's a good question. I can't think of any at the moment. One caveat, I guess I would say, is we're still living in the free fermion setting. So even though we're, I'm approximating a free fermion solvable model now by these MPS solvable models, I can't think of anything off the top of my head that wouldn't hold. But I think a more interesting question would be, how does this MPS skeleton look in the more general phase diagram of non-integrable models? And is it also dense in that case? But I agree, your question is a bit more subtle. Even if it is dense, are there properties that we can't capture with these MPS solvable models? I think my answer would be I don't know, but I can't think of anything.
Okay, thank you.
Thank you. Okay, so right, maybe let me say a little bit more about the construction about these of these MPS, maybe very quickly. So actually, how much time have I got? Okay.
You've got loads of time.
Okay, great, thanks. Right, so the way I'm going to do this is by introducing a graphical notation. Okay, so what I'm going to do is these Hamiltonian terms contain a gamma tilde and a gamma without the tilde. Okay, and I'm going to have operators which look like the exponential of these guys, and I'm going to denote them by a square and a circle connected by a line. Okay, so the square is where the gamma tilde is, and the circle is where the gamma operator is. Again, if you don't like Majoranas, you can think of this as the exponential of a Pauli string. So if the gammas are this way round, you'd have x followed by a string of z's terminated by an x. And the other example, you have y's at the end, or you could just have a z term. Right, so now what this construction says is we first start with a fixed point ground state. And now the way to do this is we start from this product state, these all down, and then we can do two layers essentially to get to this fixed point. The first is these shown in purple, and the second is a unitary layer shown in orange. Okay, so I'm not going into details of where they come from, but hopefully you can see that in that case, this fixed point Hamiltonian is just all commuting terms. It's very easily solvable, and you can easily construct the ground state with those two layers. Now, the more complicated part comes from the next bit, where we add these layers of M operators. And now, yeah, these are defined as in the result, and you end up essentially with a circuit that looks like this. So you start from a product state, you apply several layers of operators, and now in the end, what you're going to get is your ground state of your Hamiltonian. Now, to see that this is an MPS, again, I'm just going to do the same trick. I'm going to group things. So I'm going to take this gray shaded area, and now this is just a repeating element that's going to be, this is just a repeating element all the way through this sequence. And these are connected by essentially these qubit lines that go from one to the next. Okay, so again, we have this picture of, this is one of the MPS matrices, this gray block, where you have some incoming qubit lines and some outgoing qubit lines. And this is the bond dimension of these matrices. Okay. Now this particular grouping, as I've done here, is actually very suboptimal. Okay, so we've got this massive, really long grouping all the way across the page here. It turns out that we can reduce this a lot, and we can actually come up with a bond dimension that we found to be optimal. Okay, And what I mean by optimal is that it is the lowest upper bound. So while there may be certain states along the path that have a lower bond dimension, in general along the path, that's the lowest bond dimension that you could have. And the way that we get this is essentially using a nice graphical notation where we can use commutation properties of these gates. So if we have gates like this where there's no overlapping symbols, then we can actually commute them past each other. And this just follows from the commutation properties of these Pauli strings. So it's quite easy to check this. You can also commute a circle past a square and a square past a circle, but you can't commute, say, squares past squares. Okay, so this very simple graphical notation gives us an easy way to keep track of how we can manipulate these gates, how we can commute them past each other. And by playing games like this, we can actually bring it into this super simple form, like so. So this is exactly the same picture. So it's exactly the same state. It's just this guy. I've done some rearrangement, and I end up with this guy here. Now, in this case that I'm showing, this was actually bond dimension 16 in this, which I've shown in this table. If you change the parameters in your Hamiltonian, you had this p value, which was this z to the p out front, and d is essentially the range of the remaining part. We end up with this table of bond dimensions, which we've checked against DMRG. Basically, we've tried the best we can with DMRG, and we can't beat this formula that we found. And we also have some other results for specific points where we know this is the optimal case, the optimal bond dimension. All other cases, we just have this numerical evidence that this is the optimal bond dimension. Okay. So maybe let me just go through this in a little bit more detail. Maybe this is helpful if these circuit diagrams aren't making too much sense to you. Maybe it's not. But yeah, okay. Let me go through this. So what I'm going to do is I'm basically going to go from this horrible picture here to this nice and neat picture here, where we have a low bond dimension MPS. So the first thing we can do is we can use the commutation of these gates past each other. Use that here. Basically what I do is I bring the purple, orange, and green, green, and blue. Basically I bring these all next to each other, and I end up with this second step. Now the next step uses the fact that this orange gate, which I've denoted with a double line, and the reason I've denoted it as double is because it's actually a unitary gate, whereas the rest of them are not necessarily unitary. Now this one has an extra property that I can now reduce the length of some other gates by bringing them past. So I illustrate this down below. So if I have these squares lined up, then I can actually bring the orange guy past and reduce the length of the green guy. Again, this is, you can make this all very rigorous, which we've done in the paper, but it's very easy to do with this graphical notation. So I bring this orange guy past, I've shrunk some of these gates now, and I end up with this third panel. The final trick is to just do some more commuting of these gates and bring them into this neat form. Now by grouping them, I see that I have just 4 legs connecting the blocks, and these 4 legs gives us the bond dimension 16. Okay, so I hope that was interesting or useful. Okay, so there are a few special cases that I'd like to mention. The first is when we can have unitary versions of this. So in general, when I draw these pictures, these gates are not unitary. But under certain circumstances, we can actually construct an explicit unitary circuit. Now this is useful because if we had a certain bond dimension MPS, I can always turn this into a unitary circuit, but this will scale quite badly, right? The depth of the circuit will scale quite badly. In particular, it will scale with the bond dimension. However, if I have a unitary circuit like this, then it will scale logarithmically with the bond dimension. So even in cases where we, in cases of using MPS, which is what classical computers are very good at, we can potentially get an exponential advantage by using quantum computers. Now, one caveat is that we know we can do this more efficiently for certain circumstances, and others we actually haven't figured out how to do this yet, apart from the general MPS mapping. Another neat thing about these unitary versions is that we can get explicit formulas for the order parameters. So these string order parameters, which I've written a little bit differently here, you can actually relate them to these BK values that you can get from this algorithm that I flashed up earlier. Okay, so you go from the polynomial, you apply this algorithm, you get these BKs, and now these BKs, they give you the string order parameters. So straight from the polynomial, we can get these string order parameters. So these results can actually be generalized a bit beyond the BD1 class. We can go to U1 symmetric Hamiltonians. So this is like a complex fermions without pairing terms. And we actually end up with the same condition on f of z, and we conjecture, but we haven't been able to show in the same level of detail that we actually have the same optimal bond dimension. And finally, there are some cases where our result doesn't hold when there's a particular condition on these BK, these values we get from this algorithm. These actually just turn out to be a measure zero set, so they're not too important because we can actually get the MPS by a limit. Okay, so this limiting MPS actually does exist and it has the same upper bond dimension. So that case is also covered by our results. Okay, so let me kind of summarize what I've told you about. So the first thing is that we've identified this dense MPS skeleton that underlies this phase diagram. Okay, and now it provides a new understanding of this previous example where we were able to cross an SPT phase transition. So I think it's an interesting history that this model and this path was found before SPT phases were properly understood. And then after we played with it, it was an extra step before we really understood this underlying MPS skeleton. So one interesting use of these MPS-solvable paths is that we can have a series of them that converges to points in the phase diagram that aren't on these MPS-solvable paths. And for example, it provides other ways to extract, say, critical scaling exponents. We found the optimal bond dimension for these MPS. So it's not just that we have an existence, we have an optimal construction for these MPS. And in certain circumstances, we can construct unitary versions, which are potentially exponentially more efficient than the classical counterparts when used on a quantum computer. So as an outlook, what we would want to do is extend this to other symmetry classes. That might be the simplest extension of this. So we can do BD1 or this A3, but there are also other classes, say for instance, this class D, which has complex hopping, where the story is far less obvious how this construction would work. And then a far more interesting and more realistic case is, what about interacting systems, non-integrable models? Does this picture of MPS skeleton still hold? And are they still dense? And can we tell physical properties of models from these MPS skeletons? Can we also go to higher dimensions? So here we were focusing in 1D. the extension to high dimensions is interesting and also a lot less obvious.
I don't know why it keeps doing that.
Sorry. So is there a question?
I think there's some issue with the audio. Maybe somebody launched a previous video or something.
Okay. Okay, I'll carry on. So we're also interested in the connection to.
Well, I think they have a delayed feedback.
Okay, I think it stopped.
Okay, my computer seems to have crashed.
Okay, I can still hear you.
Can you turn your mic on, please?
Yeah.
All right, I think it's all okay now. Okay, so yeah, I was just saying there's also connections to Gaussian MPS and Gaussian PEPs, which we have begun to understand, but there's still many questions about the exact relationship between our MPS-solvable models and these Gaussian MPS. And one outstanding thing is to find this efficient unitary construction for all cases. And again, I'm stressing this because we could potentially get an exponential improvement over using MPS on a classical computer. And again, if this is dense, then this can hopefully push us into places where MPS can't reach. Okay, and then I'll leave you with this slide, and thank you all for your attention.
Right, shall we do it? All right. Thank you, Adam. I think our chairman has some audio problems, so let me just step in. Thank you for a very nice talk. Yeah, let me also hang on a question. So, I mean, you say that you can approach some non-MPS solvable model by the sequence of these MPS solvable ones, right? But so I guess so in general, this might require very long-range attractions, right? I mean, if you have some general polynomial, you'll end up with essentially an infinite series, if it's say square root, right? Or some other simple function that has some Taylor expansion with infinitely many terms. And of course, you can probably truncate that to get some accuracy, but if you want the exact thing, then you essentially get infinite range and hence infinite bond dimension, I guess, right?
Yes. So actually, in this case, like the transverse field Ising model, what happens is you get the transverse field Ising model plus some long range term. Now, interestingly, this long range term, first of all, the range increases, but also there's a big gap to the transverse field Ising model. So you have, the first and second term, then you have a massive gap, and then you start getting some long range terms further down the line. And so eventually they're just all getting pushed to infinity, and then all you're left with is the transverse field Ising model. So I think this was kind of interesting. It's not like you're getting all of the long range terms and then they're all kind of fading off.
Can you say something about the relative magnitude of those terms? I mean, is there some
so these are all also decreasing. I think it's going to be, I want to say exponentially with the range.
Okay, in which case that means, yeah, I mean, you can just I mean, we already know, of course, that MPS can approximate to exponential accuracy if you have a gapped phase in 1D, right?
Yeah.
Okay. Yeah, I don't know. Let's see if somebody else has some questions. So are there any questions in the audience? Or in our lecture hall, which seems to be distressed.
I'll come and ask mine.
Oh, sorry. Yep.
Okay,
Hi, Adam. Very nice talk. Can you just clarify something with your circuit there? Is the implication if I start in the ferromagnetic state or the 0, 0, 0 state, it will time evolve it to the ground state of that Hamiltonian? Is that what that unitary transformation does?
I wouldn't say it's necessarily. I wouldn't necessarily say time evolving. I'd say, yeah, I'd say it's doing, you know, some transformation to get us there. There is this interpretation that it's a sequence of imaginary time evolutions of fixed time. So these imaginary time evolutions, they can't change the phase, but then we start with this initial you know, fixed point wave function.
So the final state would be the ground state.
No. So it's not. Well, yes. So the final state, yes, would be the ground state, but it's not the ground state of these imaginary time evolutions, if that makes sense.
Right. Okay. So it's it's the ground state of the matrix product state.
Yes.
Okay. Very good. Thank you.
Yeah. It's just kind of an interesting observation that by imaginary time evolution with these different Hamiltonians, this is actually getting us where we want, the ground state of a different model.
Yeah, thank you. And thank you for a very nice talk. We have plenty of time for questions and discussion. So please, anybody with a question, either raise your hand virtually or type something into the chat and I'll go through them. I have a question as well. So you started off by emphasizing that this was in the BD1 class with these symmetries. However, the only thing I saw where that was relevant is that's because the Hamiltonian you happened to write down for this case was with that symmetry. I didn't see anywhere within it where these symmetries played any role whatsoever. Maybe you could say, is there somewhere deeper where the symmetries were coming in, or?
Yeah, this was more for the steps for how we got to the results. So one of the steps in between was showing that the Hamiltonian on these points is on these paths is frustration free. So then this form of the Hamiltonian becomes more important. Yeah, but then, like you say, if we go to this, there's also this A3 class. We can get to this one because it's actually the BD1 class where we have a 2-site unit cell. If we go to, say, this class D, then I think there might be more complications because we now have complex parameters coming in, and this frustration-free property I don't think is quite as simple. So it's probably hard to appreciate from what I've told you where this comes in, I would say.
My question was actually more fundamental, that it's,
okay.
I mean, you can certainly write down frustration-free Hamiltonians that are not in the BD1 class. And usually when you're talking about frustration, you don't talk about the BD1 class at all.
Yes. Yeah, so
it may happen, but that's a side thing. It's not like in the classification of topological phases where this is crucially important in connecting one state to another without closing a gap. So, I mean, my question was more fundamental, that you write down certain Hamiltonians, but was there anywhere within what you did where it was essential that the Hamiltonian stayed within this symmetry class rather than stayed within the particular form of Hamiltonian you were using at that moment?
I think the answer is no. I don't think it is important. I think this will hold more generally. Where it was important was for the details to get our result. So yeah, I think this result holds more generally and is not reliant on these symmetries. That's what I would say.
Okay, thank you.
Thank you.
So other questions? I mean, I have some more as well, but other people should chip in. Okay, Piers has one then.
I'm going to just type it in and you're going to read it out.
Okay, fair enough. You could try putting this beside you.
Try that, yeah. Can you hear me?
Not very well.
Okay, then.
So what about higher dimensional versions of tensor product state systems that could be exactly solved this way? Do you have any examples?
So there, yeah, it's much less clear of how to proceed. I think the biggest inspiration would come from these Gaussian PEPs. So here there's, yeah, we can understand some higher dimensional systems through these Gaussian PEPs. But this MPS picture, for example, is not going to hold, at least so simply, in higher dimensions.
Thank you.
Okay, I don't see any other questions in the chat or hands up, so I'll ask another one now, which is actually a very naive question about this quantum simulation.
Yeah.
So from an old school theorist, the idea of using a quantum computer as quantum simulation is very much that you put in a Hamiltonian and find the ground state. Whereas what you're talking about, you seem to already need to know the ground state in order to put it into the quantum computer. So in this sense, could you just perhaps explain briefly why doing this at all is useful? If you already can analytically write down the ground state, why do you need to simulate it on a quantum computer?
Yeah, that's a very good question. So one good reason is that these are kind of representative states, like the AKLT state. This is a representative state, and we should think of this maybe as a starting point. So once we're on this black path, we can now apply a series of unitary gates that preserves the symmetry. And this will keep us within the same phase, but it will move us off this black path. We'll no longer have this, the same MPS solvability. And by doing this, we can move more and more into like the more physical parts of this phase diagram. So I'd say that's one use of this as kind of like a starting point for simulations. Yeah.
Okay, thank you.
But then also, sorry, there's one extra thing. We could then, much like we do with classical numerics, we could do something more general where we have an ansatz like that looks like this, where we optimize and we actually find the ground state. Okay, just like we do with MPS, we can have these ansatz, which I want to say again that these circuits, they are actually a subclass of, I don't think I did say this, but they're a subclass of the MPS, right? So they're much shallower circuits than you would get for a general MPS. And so we can find the ground state and we can analyze these properties on a quantum computer. Whereas if we were to do this on the classical computer, we would have to do the full bond dimension MPS. And so this could be prohibitively costly on the classical computer.
Okay, thank you.
Thank you.
Any more questions?
Yeah, maybe something about the string order parameters. Do these string order parameters always end up being perfectly local? So I mean, is it a string with basically connecting two sides, or could you get something more general where maybe you have some local operator that spreads over a couple of sides and then some string in between? Could that become an order parameter, or is that just never happening?
Sorry, I'm not. So I don't think I fully follow.
Yeah. Okay. So usually, I mean, okay. So let's say Holiday model or something, right? Okay. Yeah. So you have some sigma x here, and then string of sigma z's in between, and then sigma x at the other end, right?
Yeah.
But you have two one-side operators at the two ends with essentially a string of identical operators in the center, right? So now my question is that the general form, or do the generalizations do something maybe to a couple of adjacent qubits on one end, and then you have a string of identical operators, and you have a couple of identical qubit, or a couple of operators acting at the other end.
So actually, in this case, this simple example, we have one of these. So we have, a pair of operators acting at the end, and then we have our symmetry operation. So it doesn't have to be a single operator, no. It doesn't have to be a single site operator at the end.
And I mean, is there a simple way to see that in this polynomial representation, or is it just incidental?
I'm not too sure if there is a simple way, but I mean, finding these operators at the end, this is well known, and this comes back to this. Using the MPS and the actions of the symmetry group, you can figure out what these operators at the end should be.
Okay, I think Piers had another question.
Okay.
Can you hear me?
Yes, quietly. I'll try.
Okay. Could you just illustrate how to derive the matrix product operator for the simple case of the AKLT model? Would you better do that? Since it's the simplest possible example.
Yeah, so actually in that case, that's a spin one model, right? So it wouldn't follow directly from our construction.
Well, what would be the simplest? I was just seeking the simplest example that you could.
So the simplest example is actually, the simplest example toy model is exactly this one, actually. So this is actually the simplest case. It's the square of a polynomial where it's only got one root.
But to follow you, we need to go right into the details of your analysis that you presented here. I was just wondering, was there something very simple that you could show? If I have a pencil paper in half an hour or an hour or so, I can go through your calculation and derive what you have. But is there a simple example where you can show real time how it works?
What do you think?
That's why I was asking about the AKLT model, because you introduced it as the simplest example at the beginning.
Yes, no, I appreciate that, and it would be a very worthwhile thing for me to sit down and think of an example like that, but I have not done that in time for this talk, unfortunately. Thank you.
Okay, I have another question now. So you said that every point on this phase diagram is arbitrarily close to one of these solvable lines or skeleton points or whatever.
Yeah.
But that's not necessarily of this Hamiltonian. That will be a more generalized Hamiltonian and therefore could be of a higher bond dimension.
Yes.
Okay, so is there any way you can say how many points are close to something of a given bond dimension? Because perhaps it's not that surprising a statement that every point is arbitrarily close to something of finite but arbitrarily large bond dimension.
Yes, no, that's a very good point. So yeah, if you fix the range of the Hamiltonian, or equivalently you're fixing like the maximum bond dimension for your MPS paths, then you're going to get something that looks like this diagram, right? You have, essentially a measure zero set of points within this phase diagram where it's solvable. So yeah, really to get this closeness, you need to increase your space to this full BD1 class to be able to get closer. I don't think I can. Yeah, I mean, if you're talking about this like a fixed phase diagram, then yeah, it's kind of measure zero, right? Like nearly all points are not on these MPS solvable paths.
Okay, thank you.
Thank you.
Any further questions?
Yeah, I mean, to follow up on that, I mean, does the distance from this path imply something about the likely error that your MPS representation is going to have? So let's say, you have some bond dimension 2 representation, right? And okay, so if you know how far you are from this curve, can you estimate, how big is therefore the numerical error or so, right?
Yeah,
the same with bond dimension 2.
I think the answer to that would have to be no, just because let us consider this point where I'm at the meeting point of all of these phases. Now, this is a bond dimension 2 state, whereas if I move slightly off, I am now a critical system. Okay. So, I mean, that to me sounds very different to if I sat at this point H0, H2, where it was H0. If I sit at this H0, it's a product state. And if I move very slightly away, it's only slightly different to a product state. So I think these two cases it's going to have probably quite a different dependence on how far away you are from this line.
Yeah, but I mean, of course, there are some special cases, right? I mean, when you represent a cat state or when you represent a product state, I mean, these are two kind of special limits of an MPS representation, right? I mean, yeah.
Yeah, but yeah, but just from these two examples, it's clear that you're not going to have the same dependence on what information you need, depending on how far away you are from this line.
Yeah, I mean, maybe there's some information in the polynomial or something you can say about it.
Sure, there's certainly a lot of information in this polynomial. That goes beyond what I'm talking about here. There's quite a few works, particularly by Rubin, that investigate the properties of these polynomials.
I see.
So yeah, there's certainly a lot you can know from these polynomials.
Okay.
So actually, I mean, I have another question sort of on your outlook, if you're happy to talk about that. I mean,
yeah.
So could you explain what is the connection to Gaussian MPS here?
So yeah, so when we were writing this, we became aware of some work by others, particularly Norbert Schuh, who, when reading, they had conditions that looked very similar to ours, but from quite a different language. So actually, it did turn out to be very closely related, although, for instance, the MPS construction was not available in the literature to begin with. So yeah, our method, our results are more constructive, but there is definitely a connection to results from Gaussian MPS, and in particular, these conditions were there in some other form in that case. And now motivated by that, there are works on Gaussian PEPs, and so can we use this to go beyond 1D potentially? Did that answer your question? I think beyond that, that's the question we'd like to ask. What other connections are there to Gaussian MPS, and how can we use this?
But on Gaussian MPS, you don't generally have a short range structure, right? So you can have basically these Gaussian correlators between any sides on the lattice, right? Whereas yours are, I mean, they're kind of short range-ish gates, right? So it's a bit surprising that there's a connection in a way. But...
Yeah, so yeah, I don't want to say too much in fear of getting it wrong, but I feel like this is probably a subclass of Gaussian MPS where these results were found.
Okay. So Gaussian MPS is actually the more general supergroup.
Well, again, I wouldn't want to.
Well, who knows? Maybe.
Cool. Can I also ask something on this outlook? That, I mean, you said you'd like to look for these in interacting systems. Have you had any luck with that so far?
No is the short answer. Yeah. But yeah, this would certainly be the more interesting case.
So if I don't see any other questions, and I think we're beginning to get close to the end of time. I mean, well, time for the talk, not the end of time in general, but if there's no further questions, then let's thank Adam again. We didn't manage to do it at the beginning because of our technical difficulties, so let's actually...
Thank you very much.
For that fantastic talk through skeletons of systems. So the next talk, the final talk,